start of chapter 3. Chapter 3 is a continuation, so a lot of the stuff we talked about in the last chapter is going to be used in this. I had mentioned in the previous video on the first starting day that we're going to talk about inorganic chemistry, which is a broad spectrum chemistry, and we talk about water, we talk about a lot of different elements. Organic chemistry is going to be focused on one particular element, and that is carbon. It sometimes is referred to as carbon chemistry. And once again, it's probably in your thought process why we're talking so much about chemistry, but it is the basis and foundation of biology is carbon. We are carbon-like forms. So we have to know a lot about this element in order to understand why our body and every living thing kind of relies on it. So looking back, organic chemistry you can define right here as carbon-based chemistry. And it's really focused on living things because we are carbon-based organisms. And some things let's recall about the carbon element. If you can remember this, the square on the periodic table, you would write this as carbon 12-6. That's the one on the periodic table, so let's get some information from it. The atomic number, based on that isotope form, the atomic number is 6. Atomic mass, from that form, we know the one that we'll be speaking about and most common form is carbon 12. Number of protons is always equivalent to the atomic number, so you should be able to fill this in automatically. This is completely reviewed. So we have 6 of each of them. Valence electrons, it is in column 14, so that means that we've done the Lewis dot structure enough to realize that carbon would look like this, say 4 valence electrons. That means that it's going to share 4 times. So you will always have, for example, when carbon bonded with hydrogens, and you built that molecule, notice there were 4 bonds all the time. This is the basis for why it's our carbon-based life form, because it's so versatile. It has the most number of bonds that any atom would actually bond for. So 4 of them is pretty versatile as opposed to hydrogen, which only has 1. You wouldn't want to base something on having the center. It only can bond 1 time. All right, not very good. We start simple, and the first term that we're going to look at is organic molecules. Organic molecules will be anything that has carbon in it. Most often, organic molecules also have hydrogen in it as well. It's kind of a basis for carbon-based chemistry. Simple hydrocarbons. So a hydrocarbon gets its name because it's simply a molecule that only contains carbon, and guess what other element? If you said oxygen, you're wrong. It's hydrogen. A simple hydrocarbon contains something called a carbon skeleton. It is a chain. A carbon skeleton is going to be defined as the longest chain of connecting carbons in this hydrocarbon. The carbons link together like rings on pearls on a necklace, and the analogy of that. So what you do is you have successive carbons that bond to each other. So a carbon skeleton is the longest, I'm going to have you write it because it's so low, the longest chain of connecting carbons in the hydrocarbon. So we're going to do some examples and show you where the longest chain would be. We're going to start easy where it is only a chain, so it's not going to be difficult to find, but we'll show some examples where there are some distractor carbons that are part of the hydrocarbon skeleton. All right? So the next thing is a term that is close to the word isotope. We have the word isomer. Many students, once they learn this word, get the 2 words confused. An isomer would be something that has it's 2 compounds that have the same chemical formula. It kind of starts as an isotope. You hear that starting like an isotope was 2 atoms of the same element, but they have something different, just like this. They have 2 of the same chemical formula, but different structure. And what that means is you can have 2 elements, such as C6H12O6. We're going to talk a lot about this formula a lot. And this is the chemical formula for 3 different molecules: glucose, fructose, and galactose. What makes these three different elements, or three different molecules, is the fact that the position of the atoms is completely different. They have the same formula, but they have a different structure to them. The atoms are positioned in different ways to give them different chemical properties. That's an isomer. So don't get it confused with an isotope. The word iso has that similarity where it has something the same, but it's also something structurally different. So that's an isomer. The categories that you're going to talk about tonight in this lecture, and then you're going to practice tomorrow in class. There are three different groups of hydrocarbons. The first group is called an alkane. A-L-K-A-N-E. An alkane is a hydrocarbon. Hydrocarbon that contains only single bonds between the carbon skeleton. Right? So, for example, I'm going to build a carbon skeleton that has connecting carbons. So you see how all single bonds connect these carbons. This is the carbon skeleton that has 5. Notice how there's only one bond between this carbon and this one, so this carbon still has 3 other bonds that it forms. So what it forms with, I'm going to draw the bonds. Notice every carbon every one has to have 4 lines coming off of it, so count all of these, and notice every one has 4. 1, 2, 3, 4 for this one. This carbon, 1, 2, 3, 4. These all get filled in as the hydrogen component. So this is an alkane because it's connected. Here's the carbon skeleton. It's the long consecutive chain of carbons all connected via single bonds. You're going to now start to learn how to name these carbon skeletons. This is an alkane. The first thing is we work with a prefix. The prefix is dictated by the number of carbons in the carbon chain. You can write these down. I'm going to go through from 1 through 10. If it has 1 carbon in the carbon chain, so for example, there is a 1 carbon chain. The prefix that is associated with a 1 carbon chain is meth. It's a prefix, so we're going to end it with something else, but it starts with M-E-T-H, so write that down. 1 carbon, meth. 2 carbons, which I'm not going to draw all these, a 2 carbon prefix would be F, E-T-H. A 3 carbon is prop, P-R-O-P. 4 carbon is but, B-U-T. 5 carbon is pent, P-E-N-T. 6 carbon is hex, H-E-X. 7, a lot of you will get mixed up because you're going to bring in like different foreign languages. It is hept with an H, H-E-P-T. I will tell you, most often when students forget it, they say sept with an S. Please get that out of your head right now. I know you're going to do it, so make sure that is a conscious effort. H-E-P-T is the correct prefix. 8 is geometric shapes like OC. O-C-T is 8. Known, N-O-N, is 9. And dec is 10, D-E-C. You have to memorize those prefixes, and yet as sooner you get them in there, the easier this all becomes. So this is meth as a prefix. What is the prefix for this one? According to the chart that I just gave you, 1, 2, 3, 4, 5. So therefore it is pent. To fully name this molecule, we now have to look at what the actual name of the group is. It's all single bonds. The ending on the group is the ending associated with the name down here. So the ending alkane has the suffix A-N-E. The suffix on this is going to be A-N-E, which is the same suffix as the group it belongs to. So this molecule is pentane. P-E-N-T as the prefix for 5 carbon. A-N-E tells you it's an alkane. It has all single bonds. You're going to have to go back and forth between these. I will sometimes give you the drawing and you'll name it. Other times I will give you the name and you'll have to draw it. So what will happen is, so let's, for example, if I said butane, analyze the name. BUT is a prefix that says there's 4 carbons, and the ending ANE tells you, for all purposes right now, that's the only one you know, has all single bonds. So if I told you to draw this, the simplest way to do it is to draw the carbon skeleton first. There's 4 carbons. Now start to fill in to make sure that every carbon has 4 lines or bonds coming off of it. Then you start filling them in with hydrogens. So I'll stop there, but you can continue. That is butane. A 4-carbon, single bonded from every carbon in the chain, hydrocarbon. Simple enough. That's the easiest of them. So let's progress. The second group are called alkenes. A-L-K-E-N-E-S. This is defined as a hydrocarbon that is going to have at least 1 double bond in the hydrocarbon chain. So let's show what that would mean as an example. You can write that definition down. Has at least 1 double bond in the hydrocarbon carbon skeleton. So here's an example. Notice I'm going to put a double bond right there, so that limits how many hydrogens could actually be attached. Carbon can only have up to 4 bonds, so I've already used 2 of them to connect the 2 carbons there. So this one is only going to have 2 connections of hydrogens. How many available hydrogens can be attached to this carbon? According to this, there's 2 here and 1 here that's already drawn, just based on sharing with carbons. So this one only gets 1 hydrogen. You've got to be conscious of that. Don't just start filling in hydrogens everywhere. This one, because there's only 2 bonds, will get 2 hydrogens. This one as well, 2 hydrogens. The N carbon only has 1 bond so far, so in order to fill its octet role, we need to fill in with 3 hydrogens. The prefix, once again, is the same based on the number of carbons that are in the chain. So this is going to be a pent. Okay, keep with that rule. The ending goes with the ending of the group, which is ENE. So the name of this molecule is going to be pentene. Okay? It's that simple. Pent, prefix 5, ENE, because it has a double bond. That double bond means it's in this group, the ENE, the alkenes, so therefore it looks like that. You can build butene. You can build octene. So you can think about those. We're going to draw them in class tomorrow, but I want you to have an idea of what this stuff looks like so we can do more practice in class with me present. Alright, it's going to be much easier as we progress through. The last group that we're going to do today for this video are the alkynes. Notice the ending changes. Now it's a YNE. You can probably assume where this is going. This is going to be a hydrocarbon that has a triple bond in the carbon skeleton. So let's draw an example. I'm going to keep with that same prefix so that you see the similarities between all 3. Triple bond, the sharing of 6 electrons or 3 pairs. How many hydrogens get connected to this carbon? There's only 1 more opening. So let's draw. It doesn't matter what side it gets drawn on. I'm not that picky. This carbon doesn't have any hydrogens because it already has 1, 2, 3, 4 lines coming off of it. So no hydrogens. This one, we're back to only having 2 bonds. So this carbon, the third one, will get 2. This carbon gets 2. And this one gets 3. Eventually we'll get good enough, and I'm not going to actually require you to write hydrogens. I will just assume wherever there's a line to nothing, it's assumed that there's a hydrogen there. It just gets to be a little crowded when you do multiple ones of these. But to start out with, I'm going to be very diligent about adding all these hydrogens. The name of this, can you guess what it would be? If you guessed P-E-N-T for pent, 5 carbons, Y-N-E, you are correct. The Y because that's how the ending of the group, that's the suffix of the group, the alkynes. So this is pentyne. Pent, 5 carbons, Y-N-E because it's a triple bond. If you understand this concept for this video, we will progress very soon and very easily tomorrow in class. There are some other small details that I want to fix, and we'll do some exceptions to rules and things, but I want you to get that information for tomorrow, and that's all you need. Okay, hopefully you understood it. Tomorrow you'll get your packet so you can kind of fill in the notes that would be along with this packet. All right, thanks. See you tomorrow.